Hello, everyone. Welcome back. Today, I'm going to be talking about the average rate of change. Okay, so for average rate of change, this has to do with the slope of the secant line, and that's a line that passes through 2 points on the curve. So the slope of the secant line is very much the same as any slope, right? We know that any slope is equal to delta y over delta x, or rise or run, whichever you prefer, right? Or given a function f of x, then the slope of the secant would be f of x2 minus f of x1, right? So those two y values, or f of x values as we're calling them, over x2 minus x1. So the average rate of change is really very similar concept to just the regular slope that you learned in grade 8 or grade 9, which is the good thing here. So this topic is not too bad, I promise you. Okay, so example one says the graph shows the distance in kilometers that a car has traveled over time. What is the average rate of change in the distance between the hours of 0 hours and 2 hours? Okay, well let's see. At 0 hours, they have traveled 0 kilometers, which makes sense. If they haven't spent any time on the road, they won't have gotten anywhere yet. And after 2 hours, looks like they've traveled 200 kilometers. So we need to find the average rate of change between those 2 points, okay? Which is going to actually be just the same as the rate of change overall on this line, because this line is just a straight line. Now, let's say it wasn't a straight line, then we would find basically the straight line that goes from point A to point B, which still gives us the average rate of change, right? So we'll talk more about that in the next one. But yeah, let's just answer this question. So the average rate of change is going to be the slope of the secant line, which in this case does happen to be the slope of the line, and that's going to be 200 minus 0 over 2 minus 0, and that's going to be 100 kilometers per hour. So on average, throughout the first 2 hours of their trip, they traveled 100 kilometers per hour. Now, what about the average rate of change from 2 hours, so starting here, and going up to 5 hours to here? Well, as you can see, there's some different rates of change because at first they didn't move at all. They perhaps took a rest stop, and then they traveled at a slightly lower slope, and then they traveled at a really high speed, right? So they traveled three different slopes. But we don't want to find all three of these slopes. We just want the average rate of change, that on average from the time 2 hours to 5 hours, how fast was their speed on average? Okay, so that would just be the same as the slope from here to here, right? That would be the same thing there. So let's do that. We have 500 minus 200 over 5 minus 2 here, right? If we take these 2 points and we find the slope between those 2 points as though it's a straight line, and we end up with 300 over 3, which is 100 kilometers per hour. Very good. Okay. Awesome. So even though they didn't actually do any traveling 100 kilometers per hour, given all the rates of change they did have, the average rate of change amongst all of them was 100 kilometers per hour. But I also want to point out that not every rate of change was expressed at the same value, the same frequency, right? Because it looks like only for half an hour were they going 0 kilometers per hour, right? Only half an hour for this. And then they traveled for, I think, let's see, from here to here a little bit faster than that for this rate for an hour and a half. And then they traveled at this really high speed of, I think, 200 kilometers per hour for only 1 hour, for one entire hour. And so, of course, it's not just the average of the three slopes, it also takes into account with this equation the fact that, the rest stop where they went 0 kilometers per hour, that only lasted a half hour. That didn't last as long as the other things they did. So, there we go. Now, what about the rate of change of the entire trip? You might be able to guess that the rate of change of the entire trip would just be 100 kilometers an hour as well, because for both parts of it that we looked at, it was 100 kilometers per hour. But looking at 0, 0, and 5, 500 can also prove this, right? We can find it this way, is going to give us 100 kilometers per hour. So their average rate of change throughout the entire trip was 100 kilometers per hour, even though they only actually drove at that speed for the first 2 hours. There, other times in the trip they traveled different speeds, but on average it was 100 kilometers per hour, given that after 5 hours they had traveled 500 kilometers. Very good. Let's move on to example 2. Example 2 says that a Bunsen burner is used to heat water in a beaker. The table shows the temperature every 5 seconds. The graph shows how the temperature T degrees Celsius of the water increases with time T seconds. At 80 seconds, the water reaches 100 degrees Celsius and begins to boil. Part A says determine the average rate of change from B to C. Okay, so B is this point here. It's kind of hard to see on this graph, but it's 3080. So it's this point right here is B. And then C is this point here, which is 50 and 91.4. So in this case, we actually have to use the table, because who would be able to tell from the graph that that's 91.4? Maybe we could estimate that it's about 91 or 92, but we're not going to get the exact value. So it's important that we have this table of values, because the graph is a little bit unclear. Okay, so let's find the average rate of change, which is the slope of our secant line. That is going to be delta y, or delta t, over delta of small t for time. And that is going to be 91.4 minus 80 over 50 minus 30, which is 11.4 over 20. And what's that in just kind of a nicer decimal? That's going to be 0.57. So there we go. Okay. Now, what about the average rate of change from A to D? So the thing is, from C to D, we have a not very steep slope, but we have a really, really steep slope from A to B, and that's a lot. And so I'm expecting this average rate of change from A to D to be on average higher than the average rate of change from B to C. Just looking at it, this looks steeper than this line here. So we're expecting a larger number here. But let's see what that number is. A is 0.20, so here's our A. And our D is 8,100. There we go. All right. So secant is going to be delta t over, delta small t, right, for time. So that's going to be 100 minus 20 on the top, and then 80 minus 0 on the bottom, which is just going to be 80 over 80, which is 1. Right? So on average, from A to D, when the time went up by 1 second, right, every second, on average, it went up 1 degree Celsius. Whereas from B to C, it only on average went up from 0.57 degrees Celsius per second. Actually, I should write the units, it's degrees Celsius per second for both of these. And so the average rate of change from A to D was a higher average rate than just from B to C. Right? B to C is part of A to D, but this particular part has a smaller average rate of change than the overall function from A to D. Very good. Okay, let's move on to a third example here. It says the depth of a diver in meters for time t in seconds is given by this function here. Find the average rate of change for the first 4 seconds. So for the first 4 seconds, that means from 0 to 4. Okay? So that means that t, we want to find it from when t equals 0 to when t equals 4. But wait, in order to do that, we need the respective y values, or rather the respective f of t values of 0 and 4 in order to do that. So to do this, first, we must find those, right? Because remember that the slope of the secant is f of two minus f of t1 over t2, which let's put this as t2, and this is t1 minus t1. So first, we must, on the side here, we must find f of t2, and we must find f of t1. So if t2 is 4, that means we have to find f of 4, which is 0. Actually, let's give ourselves more space here. Let's give ourselves more space. Oh, okay. Awesome. So we have 0.3754 squared minus 3.375 times 4 plus 3. And if we punch that in our calculator, we get 6 times negative 13.5 plus 3, which is negative 4.5. Then for f of 0, it's just going to be 0.375 times 0 squared minus 3.3750 plus 3, which is equal to 3. And there we go. Awesome. All right, so now we have those two values. We have our f of t2 and our f of t1 value. So that means it's going to be negative 4.5 minus 3 over 4 minus 0, which is negative 7.5 over 4, which if we punch that in our calculator, that's going to give us, let's see, negative 1.88 meters per second. And the reason it's negative is because the diver is going down, right? They're going downwards, right? So we could say that the rate of change is negative 1.88 meters per second, or we could say that it's 1.8 meters per second downwards. That's the average rate of change. So I'm going to write a conclusion statement here actually and say, therefore, the average rate of change is 1.88 meters per second down or downwards, right? Or we could just say negative 1.88 meters per second as well, but then we wouldn't also say downward because that would be a bit redundant. Okay, let's move on to B, and it asks about the average rate of change between 2 and 4. Okay, so to do this, we first need to find f of 4 minus f of 2 over 4 minus 2. Now we already know what f of 4 is. We already know that f of 4 is negative 4.5 because we already found it, so there is no point in finding it again. But we must find f of 2. So f of 2 is going to be 0.375 times 2 squared minus 3.375 times 2 plus 3, which that's going to be, let's see, 1.5 minus 6.75 plus 3, which is equal to negative 2.25. Okay, awesome. So now we have negative 4.5 minus negative 2.25. Make sure, watch those negatives. That's a common mistake I see. And then over 4 minus 2, which that's going to be negative 4.5 plus 2.25 over 2, which that is going to be negative 1.13 meters per second. Awesome. Okay. So there we have it. There we have it. All right, well, that is it for average rate of change. Next time, we will talk about the instantaneous rate of change. So I will see everybody then. Good work today, and we'll see you next day. Bye, everyone.